This video is the last installment in a series of videos where we are finding the Laplace transform of piecewise continuous functions. In the part 2 video, we worked on example A. Part 3 video worked on example B. So in this video, we're going to start off with example C. So in example C, we have got f of t defined by e to the minus t in the interval t between 0 and 4, and then for values of t bigger than 4, the function is defined to be 0. So in the first method, we're just going to plug this into the integral definition of the Laplace transform. So if we do that, so the Laplace transform is the integral from 0 to infinity, but this one we first going to have the interval 0 to 4, where the function is e to the minus t. Then by definition we multiply that by e to the minus st. Then we're going to get the interval from 4 to infinity. In that interval, the function is defined to be 0. So that means this second term is automatically going to vanish. So we only have the integral from 0 to 4 of those two terms. If we combine them, this is the same as e to the minus 1 plus s dt. And in fact, integrating this is not very difficult. So we're just going to divide by negative 1 plus s. So that's from 0 to 4. Plugging 4 into this setup gives us e to the minus 4 into 1 plus s all over negative 1 plus s. Then for the lower limit, we're not going to get a plus, and the numerator is now going to be 1 because it's e to the power 0. And then writing this as one term is going to work out something like that. So that is going to be the Laplace transform of our function here. Then in the second method, we are now going to use the Heaviside function. So it is a good idea for you to master both approaches, of course, because there are going to be cases where the one is more efficient than the other. So for this function, if I just make a quick sketch, so between 0 and 4, function is defined by the Heaviside function by e to the minus t, so e to the minus t there, and then from 4 to infinity the function is 0. Okay, so what we do is we start off with this function, just e to the minus t, and then we need to multiply it by a box which is defined in terms of the Heaviside function. So the box is 1 over the interval where we want to maintain this function, and it is 0 over the interval where we want the function to become 0. So this type of box, again, we recommend you check our videos where we did a detailed discussion of how this works out, is going to be h of t minus h of t minus 4. So that means our function is going to be e to the minus t times h of t minus h of t minus 4. We remove the square brackets, so that's going to be e to the minus t times h of t minus e to the minus t times h of t minus 4. And then we already mentioned in the previous example that we want the argument of the two functions to be the same. So for instance, here it's t and t, so that's fine. Here it's t minus 4, here it's t there. So we need to work this function with this function here, so that we've got t minus 4 in that exponent. So what we are going to do is manipulate this algebraically. So we've got e to the minus t. We are going to write it as e to the minus t minus 4 plus 4. E to the minus 4 plus 4. Yes, and then so what we're going to do here is we're going to treat these as two terms. We keep that one as one term. So this becomes e to the minus t minus 4 times, if you remember your properties of exponents, so that's going to be e to the minus 4. But this is just a constant, so that is not a problem. So that means our function f of t we can write as e to the minus t h of t minus e to the negative 4 times e to the minus t minus 4 h of t minus 4. Now when it comes to taking the Laplace transform, that is going to be the term that is important. So the Laplace transform therefore is going to be, so the Laplace transform of e to the minus t minus e to the minus 4 times the Laplace transform of e to the minus t to the t minus 4. Now remember, the Laplace transform of h of t minus a, f of t minus a is equal to e to the minus as times the Laplace transform of fs. So that means in our case, for the first term, so the Laplace transform f of t, for this first term here, a is 0. So that's just going to be the Laplace transform of s, because a is 0. The Laplace transform of e to the minus t is simply 1 over s plus 1. The constant e to the minus 4 goes through the process of taking the Laplace transformation. For this one, so it's going to be a term similar to this one, but with the addition of that a is 4, so it's going to be e to the minus 4s all over 1 plus s. And then again of this we can write as one term. It's going to be 1 minus e to the minus 4 into 1 plus s. And then if you compare this with what we found using direct integration, you'll see that it is exactly the same term. Right, then for the next example, which is example number D, So in example number D, our function is defined as follows. So f of t is 0 in the interval from 0 to 0 to 1, then t squared minus 3t from 1 onwards. Okay, so 0 to 1, 0 to 1, and then t squared minus 3t for t greater than 1. If we plug this into the integral definition, so our Laplace transform is going to be the integral from 0 to 1 of 0 times e to the minus st dt. Then we're going to have 1 to infinity t squared minus 3t e to the minus st dt. The first term vanishes, this one, so we just have to integrate this one, which we can do using tabular integration, so that is going to be efficient. So we're going to have t squared minus 3t here. Derivative of that is 2t minus 3. Derivative of that is 2, and derivative of that is 0. The integral of this one, minus 1 over s, and the integral of that is in 10, this one, and the integral of this one is that. Then the first matches the second with the third, and the third with the fourth. So that means our Laplace transform is going to be, all these are going to be negative. So all these are going to be negative. So what we can do, just put the negative outside here. T squared minus 3t over s, 2t minus 3 over s squared, 2 over s cubed, and then times e to the minus st from 1 to infinity. Okay, and the limit t goes to infinity, this term is going to go to 0. Then at t equals to 1, so because the lower limit, the plus is going to go away. So what's going to happen is if we plug in 1 here, if you plug in 1 here, this is going to give us minus 2. Plug in 1 here is going to give us 1. So we're going to have 2 over s cubed plus 1 over s squared minus 2 over s e to the minus s. So that is going to be our Laplace transform using direct integration. Then using the method of Heaviside functions, so remember this time f of t is 0 in this interval, t squared minus 3t in this interval. So in terms of the Heaviside function, let me just make a quick sketch here. So this function is 0 between 0 and 1. So that means it's going to look something like this. At 1, this thing is -2. It opens upwards, so maybe something like this. Okay, so what we need is, if we just take this function as it is, then we need to hit it with a Heaviside function that is going to nullify the segment on the left hand side of 1. Okay, so we hit it with a Heaviside function that is going to multiply the bit on the left hand side of 1. So our Heaviside function must have 0 here, and then it must have 1 this side. So, and that's just going to be h of t minus 1. So that means our f of t is simply going to be t squared minus 3t h of t minus 1. Then h of t minus 1 we need to express in terms of, not h of t, t squared minus 3t we need to express in terms of t minus 1. So we can do that either using the Taylor series, or we can do this manually if you like, algebraically. For instance, this we can write as t squared minus 2t minus t. Okay, then we can complete the square between these two terms. So if we complete the square here, then it's going to be t minus 1 all squared. So if we do that, t minus 1 all squared minus t, which is this one. Then when we do that, when we do t minus 1 all squared, we must subtract 1. So that's from the process of completing the square. We still have h of t minus 1 this side. Then this is going to be t minus 1 squared minus, what we can do here is we can write this as t plus 1. But then we want it to be t minus 1. So we'll do that in a moment. So this is going to be t minus 1 squared minus. So what we are going to do is we're going to write this as t minus 1. Then the question is, what do we need to add or subtract to make this plus 1? And the answer is we need to add 2. So minus 1 plus 2 is plus 1. But then we're going to take this as one term and that is the other term. So we are finally going to have something like this. So this is now going to be t minus 1 squared minus t minus 1 minus 2. And then at that point we can take the Laplace transform. So therefore the Laplace transform of this is going to be e to the minus s into this is just going to be the Laplace transform of t squared, which is 2 over s cubed. This is just the Laplace transform of t, and of course that is just the Laplace transform of 2. And you're going to notice that this is again the same as the one we obtained before, and of course it as you can see before there was a small error here. This should be negative because it's 2 minus 3. Yeah, so that should be negative there, which we have it correctly. All right, so it brings us to the end of that video. Thank you for watching. Please do, of course, remember to subscribe and like our videos. If you've got any questions, you can post them in the comment section. Thank you.